This is the Helicopter Flying Handbook, Chapter 11, page 19 of 24, main rotor disc interference, going into page 20. Refer to figure 11.11. Winds at velocity of, let's look before we start off. Okay, so figure 11.11. Winds at velocities of 10 to 30 knots from left front cause the main rotor vortex to be blown into the tail rotor by the relative wind. This main rotor disc vortex causes the tail rotor to operate in an extremely turbulent environment. During a right turn, the tail rotor experiences a reduction of thrust as it becomes into the area of the main rotor disc vortex. The reduction in tail rotor thrust comes from the airflow changes experienced at the tail rotor as the main rotor disc vortex moves across the tail rotor disc. The effect of the main rotor disc vortex initially increases the angle of attack of the tail rotor blades, thus increasing tail rotor thrust. The increase in the angle of attack requires the right pedal pressure to be added to reduce rotor thrust in order to maintain the same rate of return. As the main rotor vortex passes the tail rotor angle of attack is reduced. The reduction in the angle of attack causes a reduction in thrust, and rigid yaw acceleration begins. This acceleration can be surprising, since previously adding right pedal to maintain the right turn rate. This thrust reduction occurs suddenly and is uncorrelated, develops into an uncontrollable rapid rotation about the mass. When operating within this region, be aware that the reduction in tail rotor thrust can happen quite suddenly, and be prepared to react quickly to encounter this reduction with additional left pedal input. Weathercock stability, 120 to 240 degrees. In this region, the helicopter attempts to weather vane or weathercock its nose into the relative wind. Figure 11-12. Unless a resistant pedal, let's go to 11-12. Weathercock stability. Unless a resistant pedal input is made, the helicopter starts a slow, uncommanded turn either to the right or left depending upon the wind direction. The pilot allows a right yaw rate to develop and the tail of the helicopter moves into this region. The yaw rate can accelerate rapidly. In order to avoid the onset of LTE in this downwind condition, it is imperative to maintain positive control of the yaw rate and devote full attention to flying the helicopter. Tail rotor vortex ring state 210 degrees to 330 degrees. Winds within this region cause a tail rotor vortex ring state to develop. Figure 11-13. The result is a non-uniform, unsteady flow into the tail rotor. The vortex ring state causes tail rotor thrust variation, which result in yaw deviations. The net effect of the unsteady flow is an oscillation of tail rotor thrust. Rapid and continuous pedal movements are necessary to compensate for the rapid changes in the tail rotor thrust when hovering in a left crosswind. Maintaining precise heading in this region is difficult, but the characteristic presents non-significant problems unless corrective action is delayed. However, high pedal workload, lack of concentration, and over-controlling can lead to loss of tail rotor effectiveness. When the tail rotor thrust being generated is less than the thrust required, the helicopter yaws to the right. When hovering in left crosswind, concentrate on smooth pedal coordination and do not allow the uncommanded right yaw to develop. If a right yaw rate is allowed to build, the helicopter can rotate into the wind azimuth region where weathercock stability then accelerates the right turn rate. Pilot workload during a tail rotor vortex ring state is high. Do not allow a right yaw rate to increase. LTE at altitude. At higher altitudes where the air is thinner, tail rotor thrust and efficiency are reduced. Because of the high density altitude, power plants may be much slower to respond to power changes. When operating at high altitudes and high gross weights, especially while hovering, the tail rotor thrust may not be sufficient to maintain directional control and LTE can return. In this case, the hovering ceiling is limited by tail rotor thrust and not necessarily power available. In these conditions, gross weights need to be reduced and an operation need to be limited to lower density altitudes. This may not be noted as criteria on the performance charts. Reducing the onset of LTE. To help reduce the onset of LTE, follow these steps. Maintain maximum power on rotor RPM. If the main rotor RPM is allowed to decrease, the anti-torque thrust available is decreased proportionally. Avoid tailwinds below airspeed of 30 knots. If loss of translational lift occurs, it results in an increased power demand and additional anti-torque pressures. Avoid OGE operations in high power demand situations below airspeeds of 30 knots at low altitudes. Be especially aware of wind directions and velocities when hovering in winds of about 8 to 12 knots. A loss of transitional lift results in an unexpected higher power demands and an increased anti-torque requirement. Be aware that if a considerable amount of left pedal is being maintained, a sufficient amount of left pedal may not be available to counteract an unanticipated right yaw. Be alert to changing wind conditions, which may be experienced when flying along ridge lines and around buildings. Execute slow turns to the right, which would limit the effects of rotating inertia, and the loading on the tail rotor to control yawing would be decreased. All right. So recovery technique. If a sudden unanticipated right yaw occurs, the following recovery techniques should be performed. Apply forward cyclic control to increase speed. If altitude permits, reduce power. As recovery is affected, adjust controls for normal forward flight. A recovery path must always be planned, especially when terminating the OGE hover, and executed immediately if an uncommanded yaw is evident. Collective pitch reduction aids in arresting the yaw rate, but may cause an excessive rate of descent. Any large rapid increase in collective to prevent ground or obstacle contact may further increase the yaw rate and decrease the rotor RPM. The decision to reduce collective must be based on the pilot's assessment of the altitude available for recovery. If the rotation cannot be stopped and ground contact is imminent, an auto rotation may be the best course of action. Maintain full left pedal until the rotation stops, then adjust the main heading. For more information on LTE, see Advisory Circular AC 90 through 95, Unanticipated Right Yaw in Helicopters. So we'll hold off there. That ended on page 21 and 24. That was pretty much your LTE and altitude, main rotor disc interference on your tail rotor, limiting your tail rotor effectiveness. So now we're going to go into, we'll go into main drive shaft or clutch failure on page 21. All right, so that we're ending right there on 21-24, chapter 11.